Hi, welcome back to Educator.com. We're going into the section called Related Rates. In the Related Rates section, it's a different application of derivatives. So it's a little more complicated than the ones we're used to, but if we keep in mind the simple definition of derivatives, we can solve these problems as well. So find the rate of change of two variables related by a third variable. So far we've only been doing dy dx, which is the change of x in relation to y. Implicit differentiation is still two variables. And now we introduce a third variable, which usually is time, usually. And on the AP exam, it usually is time. So that's why we're talking about time the most. So for these related rates problems, it might get a little messy and confusing. So we have to really think about the big picture. What are we solving for when we go zoom in on the little parts? And we have to keep our organization really, really well done. So it's a process of zooming in to look at details and then zooming out for the big picture and finally solving for the answer. So let's take a look at a simple example right away. So for related rates problems, you'll see something like this. A circle grows at a rate of 8 pi inches squared per second. At what rate is the radius growing when the radius is 2 inches? So we see that here we're dealing with a circle growing at a rate of 8 pi inches squared per second, which we know is the area. So the area is growing at a certain pace. So what rate is the radius growing? So it's a change in area and a change in radius. So dA dt and dr dt. So we see that here's our first variable changing in relation to time, area, and radius is the second. So it's very traditional, stereotypical related rates problem that you should definitely know very well. So to start off, well, what is the relationship between all these variables? That's the key thing. So the relationship here is the area, which we've given, the change in area, equals pi r squared. So that's a simple relationship. So then we take the derivative of this. Well, dA dt equals 2 pi r dr dt. So radius is changing with respect to time, and so is area changing with respect to time. Well, now we're looking for what rate is the radius growing. So that translates directly to what is dr dt. Well, dr dt, we have other variables here, but they tell us what they are. So when the circle grows at 8 pi inches squared per second, we know that is 8 pi equals 2 pi r. Well, r, when the radius is 2 inches, so zooming out, we see that, or zooming in, we see that the radius is 2 inches, so 2. And then we have dr dt, which is what we're looking for. So now it just becomes a simple arithmetic problem. Well, dr dt, solving for that, we get that dr dt equals 2 inches per second. And we have to keep in mind that this is only valid, this answer is only valid when radius equals to 2 inches. So that was a quick look at a very basic related rates problem. So let's take a look at another type. So we were just talking about the area of a circle. Now let's go into a third dimension and look at volume. So we're looking at a spherical balloon that's expanding at a rate of 30 pi centimeters cubed per second. So the volume expanding at that rate. How fast is the surface area expanding when the radius is 2 centimeters? So let's approach this problem the same exact way. We know that the volume, dV dt, is changing at 30 pi centimeters cubed per second. And we know that there is a surface area, so dA dt, which we don't know yet, and we know that the radius equals 2 centimeters. So that's the information that they're giving us. What is the relationship between all those variables? Well, the relationship here is that volume equals 4/3 pi r cubed, and the area equals 4 pi r squared. And once again, we're looking for dA dt. Well, dA dt, using red, dA dt equals the derivative 8 pi r dr dt. So do we know dr dt? Well, we don't know how fast the radius is changing, but we do have this other information. Maybe we can use that to help us find dr dt. So let's look at dv dt. Well, that equals 4 pi r squared dr dt. Well, we're still looking for dA dt ultimately, but we can use this to help us find dr dt. So we know that the volume is changing at a rate of 30 pi centimeters cubed per second. So 30 pi equals 4 pi r, which is 2 centimeters squared, times dr dt. Well, we can now solve for dr dt, which is just arithmetic, just simple arithmetic. So dr dt, solving for this, is 15/8 centimeters per second. So now we can definitely apply this to here, zooming out, and looking for dA dt. So looking for dA dt here equals 8 pi r is 2 centimeters times 15/8 centimeters per second. And multiplying everything out, we get 30 pi centimeters squared per second. So this example is almost the same as the last one, except we had to go ahead and use another relationship, dv dt, to solve for a component of dA dt so we can find the final answer. Once again, being very organized and keeping a clear mind about the whole picture, the main idea, looking for the surface area change. Another typical related rates problem you'll see on the exam, on the AP exam, is a traveling problem. So when you have two objects traveling in different directions, we have to analyze their paths in relation to each other. So one object is going to have a relationship with time that's different from the other object. So it's kind of like the same as volume change and surface area change and radius change, just different context. So let's take a look at this example. Abe is walking west at 5 miles per hour, and Bob is running south from the same spot at 10 miles per hour. So let's see. Let's draw a picture here. Abe is walking west at 5 miles per hour, and Bob is running east at 10 miles per hour. So here's Abe. Here's Bob. What is the rate of change of the distance between Abe and Bob when Abe is 2 miles from the starting point and Bob is 10? Well, when, let's call this x equals 2 and this y equals 10. What is the distance? What is the rate of change of the distance between them? Let's use red for that as our final answer. So here's the distance between them. What is the rate of change of that line? So we'll call that z maybe. So dz dt. Okay, so we know this 5 miles per hour is our dx dt, and this 10 miles per hour is our dy dt. So what is the relationship between x y, and z. Well, we see that it's a right triangle, so geometrically, the relationship is just x squared plus y squared equals z squared. And so all we have to do is take a derivative of this, maybe implicitly because the equation is quite difficult to solve for one single variable. And implicit differentiation is what we've been doing with the related rates problem, just a simplified version. So let's take the derivative of this expression, 2x dx dt plus 2y dy dt. Let's use a different color for the dx dt and dy dt. Dx dt plus 2y dy dt equals 2z dz dt, which is our final value that we're looking for. So now we need dx dt, which we know, dy dt, which we know, x, which we know, y, which we also know. So what is z? Well, let's just solve for z when x is 2 and y is 10. So let's have a little side note here. Well, when x is 2 and y is 10, z equals the square root of 104. So now we have every single variable in this equation that we can just plug in and solve for dz dt. So plugging everything in here, 2 times 2 times 5 dx dt plus 2 times 10 times 10, which is dy dt, equals 2 times square root of 104 dz dt. Moving things around and solving for dz dt, we get dz dt is equal to 10.79 miles per hour. So what this is saying is that the rate of change of the distance between them as they walk in the separate directions, west and south, is at a rate of about 10.8 miles per hour. So every hour, their distance will increase by 10.8 miles. So going to another related rates example, this time with a square involved. So let's just go ahead and draw a square to examine our relationship between the variables. Well, here is a square, kind of shoddy, but when the area of a square is increasing 3 times as fast as the diagonal, so we know we need a diagonal. So let's call this side. These are sides. So what is the perimeter of the square? Well, perimeter simply equals 4 times s. And we also know that the area of a square equals s squared. Well, what about the diagonal? Well, the diagonal is simply equal to s times root 2 by our special triangle property, 45, 45, 90. So diagonal equals s square root of 2. Well, let's call this z. So z equals s square root of 2, just for simplicity when writing. So we are looking for what is the perimeter of the square. Well, we're just looking for this. But what is the relationship between s and z? Because we are given that the area is increasing 3 times as fast as the diagonals. So what is the relationship between the area and the diagonals? Well, the relationship between the area of the diagonals is simply we solve for s equals z over square root of 2. So the area equals s, which is z over the square root of 2 squared, which is z squared over 2. So that's the relationship between area and diagonal. So this problem might not happen exactly as is on the AP exam, but all we have to do is know how to relate all the variables together. So we're given the area, we're given the diagonal. So let's find a way to relate them. And this is how we did it. by solving for the diagonal in relation in terms of s and plugging it back into the area to get it in terms of z, the diagonal. So now that we have a relationship, we know that the area is increasing, which means we have to take the derivative. So taking the derivative of this area, dA dt equals, well, this is simply 1/2 times z squared. So this is dA dt is just z dz dt. So the area of the square is increasing 3 times as fast as the diagonal. So 3 times as fast. Well, that means, in other words, in mathematical terms, the area of the square is changing 3 times as fast as the diagonal is changing. So that means z equals 3 when that happens. So z equals 3. Well, what is a perimeter? We're not done just yet. We know that z equals 3. Well, let's just plug in z back into the perimeter equation. So we know that s equals 3 over root 2. So the perimeter equals 4 times s, 3 over root 2. So our answer is 12 over root 2. Or the perimeter of the square is 12 over root 2 when the area of the square is increasing 3 times as fast as the diagonal. Okay, so looking at the next example, what is a sphere's surface area when the volume increases twice as fast as the radius? So right away, we know that for a related rates problem, we're going to have to find a way to relate the surface area, the volume, and the radius. And more specifically, the surface area, the change in volume, and the change in radius. So surface area the change in volume, and the change in radius. So we're going to probably have to take some derivative of the volume. So what is the volume of a sphere? Well, the volume of a sphere is just 4 over 3 pi r cubed. And the area is 4 pi r squared, and we know this from our previous example. So we're looking for the surface area when the volume increases twice as fast as the radius. So let's take the derivative of the volume. So dV dt equals 4 pi r squared dr dt. So we know that, well, when the volume is changing twice as fast as the radius is changing. So we kind of know that 2 equals this whole expression just by looking at the patterns of the equations. Well, let's set that up. 4 pi r squared equals 2. So solving for r is going to equal 1 over square root of 2r. So now that we have radius, we can plug it back in to find the surface area. So that is just a straight plug-in. So area equals 4 pi 1 over square root 2 pi squared is 4 pi 1 over 2 pi, which equals 2 units squared. All right, so we related all these variables that we were given or asked for by these equations, and we took the derivative of these equations because it's telling us about the change in the variables in relation to time. So this is a very standard related rates problem that you should also know. All right, so looking at one last example of related rates. This one is a little bit different from the others, but following the same principles of related rates problems in applications of derivatives, we can solve this problem just the same by saturating the details and the context into our just math model. So let's take a look at this problem. Light on the ground 50 feet from a wall. So we're going to have a wall, and we're going to have the ground. So 50 feet from a wall shines on a 5-foot tall man walking to the wall at 2 feet per second. At what rate is his shadow decreasing when he is 10 feet from the wall? Okay, so light on the ground 50 feet from a wall. So here's the light. 50 feet from the wall. So shines on a 5-foot tall man. So here's our 5-foot tall man. It shines his shadow onto the wall. Here's the wall is really, really, really tall, negligibly tall. All right. So let's put some variables in here so we can use it to solve for derivatives. Well, we're asking for the rate of his shadow decreasing. So here's his shadow. So let's call that y. And we know that he's walking to the wall at 2 feet per second. So let's denote this distance, x, and this distance, 50 minus x. So we see that there's two similar triangles. Well, how do all these variables relate? Well, if he's walking to the wall at 2 feet per second, we can call this x, we can call that dx dt. So then to relate all these variables together, we see that this is a giant similar triangle inside an even bigger one. So 5 over y equals x over 50 minus x. Oh, excuse me, x over 50. So we have now an expression for x and y. Well, we know that y just equals 250 over x is 250 times x to the negative 1. So the change in y, dy dt, is going to be negative 250 x to the negative 2 dx dt. Well, let's go ahead and plug in dx dt because we know that the man is walking to the wall at 2 feet per second. So x is changing at a rate of 2 feet per second, which is dx dt. So this expression becomes negative 250 times x to the negative 2 times 2, which equals negative 500 over x squared. So now we have this expression for dy dt and x squared, and we're looking for the rate at which his shadow is decreasing. So we're looking for a dy dt. This is what we're looking for. So all we need is to find x. So what is x? So to solve for x, when the shadow is decreasing, when he is 10 feet from the wall, what rate is this shadow decreasing? Well, at 10 feet, here's your hint. This is your x. They're always going to give you either what you need to solve the problem or enough information to help you solve for what you need. So here they're giving you 10 feet, which is x. So let's solve for dy dt equals negative 500 over 10 squared, which equals well, actually, x is not what they're giving you. So here it's a little tricky. 10 feet from the wall, well, 50 minus x is 10 feet from the wall. So actually, 10 feet is 50 minus x. So we'll have to do a little bit of arithmetic to get x. So 50 minus x equals 10. Then x equals 40. So then here we have negative 500 over 40 squared, which means negative 5 over 16 feet per second. So for this problem, we had to do a little bit of manipulation to get what we wanted. To review, we started with a relationship of the man's shadow casted on the wall. So we have a y term, we have an x term, and we're looking for the change respect to time of those variables. And we're looking for the rate of his shadow, so that's dy dt. And we solve for all the other variables based on the information given. So once again, for related rates problem, we have to just be very, very organized and keep in mind of the giant picture to get the answer that we are looking for. So thanks for watching Educator.com. We'll see you in the next lesson.